It began 13.7 billion years ago, and today it's filled with 100 billion galaxies, each containing hundreds of billions of stars. We are part of this universe, so its story is our story. This story is about what makes us and where it all came from. Because understanding our own origins means understanding the lives of stars and how their catastrophic deaths bring new life to the universe. Every mountain, every rock on this planet, every living thing, every piece of you and me was forged in the furnaces of space. Every religion in the world has a creation story. It tells us where we came from and how we came to begin, and what will happen when we die. I have a different creation story to tell, and it's based entirely on physics and cosmology. My story can tell us what we made of and where we came from. In fact, it can tell us about everything in the world, what it's made of, and where it came from. It also answers that most basic of human needs, to feel part of something much bigger. Because to tell this story, you have to understand the history of the universe. And it teaches us that the path to enlightenment is not an understanding in our own lives and deaths, but the lives and deaths of a star. My creation story is the story of how we were made by the universe. It explains how every atom in our body was formed, not on Earth, but was created in the depths of space through the epic life cycles of the stars. To understand that story, we will journey to the stars in all that stages of life. This is where stars are born, a nebula, a stellar nursery where new stars burst into life. Those stars will burn for billions of years until their voracious hunger for fuel forces them to blow up, to become giants. Hundreds of times the size of our sun. But when they die, stars go out with the biggest bang in the universe. But To understand how we came from the stars, we must begin our journey much closer to home. This is sunrise over the tallest mountains in the world. Every one of those peaks are over 6,500 meters. Spectacular sight. But it's incredible to think that just a few tens of millions of years ago, those mountains were something very different. The Himalayas. They haven't always been mountains. We can find clues to their true origin by looking at them more closely. This is Himalayan limestone, the rock out of which much of this magnificent mountain range is made. If you look closely, you can see that it is kind of a chalky, granular structure, because limestone is made primarily as of the bodies, shells, and dead sea creatures like coral. And when they die, they put into immense pressures and squashed, eventually forming limestone. So the Himalayas were once living creatures. Much of the Himalayas were formed at the bottom of the ocean, and then over millions of years it was raised up to become these vast peaks. We've even found fossils on top of Mount Everest. It's a beautiful example of the endless recycling of the Earth's resources that has been going on since the dawn of time, and we are part of that system. Every atom of my body was once part of something else, like an ancient tree may have been a rock. The reason that the rocks of Earth can become living things is because everything is made of the same basic ingredients. Those ingredients are chemical elements, the building blocks of everything on Earth. Elements like hydrogen, helium, lithium, carbon, nitrogen, oxygen, chlorine, sodium, magnesium, etc. Everything in the world is made out of the same basic set of chemicals, assembled just in different ways. So the Himalayan mountains are made of limestone, which is calcium carbonate. Calcium, carbon, and oxygen are the elements that are vital for life. We've got calcium in our teeth, in our bones. We have oxygen and carbon in every organic molecule in our body. You are probably familiar with those chemicals in their combined forms, but you very rarely see those elements on their own. There is a good reason why many of the elements are not found in their raw forms in nature. They're extremely reactive. This is sodium. As you can see, it's a silvery metal and it's also quite reactive. When you drop it into water, you get a violent, almost explosive reaction, which is all the more surprising when you think that when combined with chlorine, this forms sodium chloride, salt, which is vital for life. It's this reactivity which enables these elements to combine with one another to make new substances. That, in turn, has allowed the Earth to develop its endless variety, and that variety includes us. So to explain where we come from, we must be able to explain where the elements come from. We now know that the Earth is made out of 92 elements. That's pretty amazing if you think of the complexity we see around us. We also know that everything beyond us, everything we can see in the universe, is made of those same 92 elements around us. The chemistry set we have on Earth extends far beyond the planet. We've set foot on the moon and know that it's rich in helium, silver and water. We've sent robot landers to our neighboring planets and discovered that Mars is rich in iron, which is combined with oxygen to form its familiar rusty red color. And we know that Venus's thick atmosphere is full of sulfide. We've sent spacecrafts to the edge of the solar system to discover that Neptune is rich in organic molecules like methane. But what about the rest of the universe? It's impossible to figure out what the stars are made of because they are so far away. Even the nearest star, Proxima Centauri, is 10,000 more times distant than Neptune, 4.2 light years from Earth. And the nearest galaxy, Andromeda, is another 2.5 million light years away. Yet, despite these vast distances, these alien worlds have constantly sent us signals, telling us exactly what they're made of. Our only contact with the distant stars is their light that journey across the universe to reach us, and incurring in the light is the key to understanding what the universe is made of. And it's all down to particular property of particular chemical elements. You see, when you heat the elements and you burn them, then they give off light, and each element gives its own unique set of colors. This is strontium burning. It's best known for the brilliant reds that this element's salts give to fireworks and flares. It's also used for glow-in-the-dark paints and plastics that contain strontium aluminates. Sodium burns yellow. It is a mineral that occurs naturally in many of the foods we eat. Sodium chloride, or salt, is the most common type of sodium found in nature. It's also the type of sodium you'll find in food. Potassium burns a lilac color. Potassium is a mineral and an electrolyte. It helps your muscles work, including the muscles that control your heartbeat and breathing. Potassium also comes from the food you eat. This is copper, which burns a blue-green color. Copper is one of the few metals that can occur in nature in a directly usable metallic form. It is a soft and ductile metal with very high thermal and electrical conductivity. Each element has its own characteristic color. It's this property that tells us what the stars are made of. But it's a little more complicated than simply looking at the color of the light that each star emits. You can see why by looking at the light from our nearest star, the Sun. This is a spectrum of the light taken from the Sun. At first glance, it looks very familiar. It's like a stretched out rainbow, and that's exactly what a rainbow is, a spectrum of the light of the Sun. But if you look a bit more closely, then you can see that the spectrum is colored in black lines. These lines are called absorption lines. Each element within our Sun not only emits light to a certain color, it also absorbs light of the same color. By looking at these black lines, we can simply read of its elements like a barcode. For example, these two black lines in the yellow bit of the spectrum, that's sodium. And you can see iron in the far right green area. So by looking at these lines in precise detail, you can work out exactly what elements are present in the Sun. And it turns out that it's about 70% hydrogen, 20% helium, and 2% the rest. You can do this not only for the Sun, but for any of the stars you can see in the sky. And you can measure exactly what they're made of. That star over there is Polaris, the northern star. It's 430 light years away. And you can see all the other stars in the night sky that rotates around it. But we know by just looking at the light that it has about the same heavy elements abundance as our Sun. But it's got remarkably less carbon and a lot more nitrogen. And the same applies for other stars. Vega, the second brightest star in the northern sky, has only about a third of the metal content of our Sun, whereas other stars are metal heavy. Sirius, the dog star. It contains 3 times as much iron as the Sun. Proxima Centauri is rich in magnesium, but although the quantities of the elements they vary, wherever we look across space, we only ever find the same 92 elements that we find on Earth. We are made of the same stuff as the stars and the galaxies. But where did all this matter come from? And how did it become this complex universe that we see today? In order to understand where we came from, we have to understand events that happened in the first few seconds of the life of the universe. See, when the universe began, it was unimaginable hot and dense, but it was very beautiful. There was no structure and no matter. It was exactly the same whichever way you looked at it. We can get some idea of how the universe developed from its state of pure symmetry by looking at the behavior of water in this remarkable landscape. These are the hot springs. As the boiling water bubbles up through the ground to meet the freezing mountain air, water can be found in its all three natural phases: vapor, liquid, and ice. In its hottest state, water is like the early universe, an undifferentiated cloud. But as it cools, it suddenly behaves very differently. If you look at the cloud of steam, it looks like the same from every direction. But as it cools down, as it lands on this freezing cold glass, it immediately crystallizes and turns into solid water, ice. As the ice crystals fall, the symmetry of water vapor disappears, and a complex, beautiful structure emerges. In the same way, we think that when the universe as it cooled, it went through a series of these events where structure emerged. One of the most important was like a billionth of a second after the Big Bang. In that moment, an important part of the symmetry of the universe was broken, known as the electroweak symmetry breaking. This was the moment when saboteur particles acquired mass substances for the first time. Amongst them quarks, as the universe continued to cool, those quarks joined together to form larger, more complex structures called protons and neutrons. Way before the universe was a minute old, the quarks have been locked away inside the protons and the neutrons. They are the building blocks of all atomic nuclei, the building blocks of the elements. These same protons and neutrons are with us to this day. They form the hearts, the nuclear heart of atoms. A few seconds after the beginning of the universe was the fundamental building blocks of everything that have been created. But it sounds ridiculous that everything you need to make a human, and everything on planet Earth, in fact, every star and every galaxy in the sky, was there after the first minutes of the life of the universe. It's almost unbelievable, but we have extremely strong experimental evidence that suggests that that is the way that it is. But from that point on, there was just assembling those bits to create more and more complex things. That is an incredibly fascinating story in itself. To tell that story, we must look deep inside the atom, to the nucleus of its center. Here we can see how protons and neutrons are assembled to build up the 92 different elements. Now, the wonderful thing about the construction of the chemical elements is that it's so simple. I suppose you could call it child's play. So imagine these bubbles are a universal chemistry set. The single bubbles could just be single protons. That's the nucleus of the simplest chemical element. The element with a single proton in its nucleus is hydrogen. And from hydrogen, you can make all the other elements. The first stage is to stick two protons together, like two bubbles. What happens when you stick two protons together? One of the protons turns into a neutron, and that is called deuterium. Deuterium is still a form of hydrogen because it has only one proton in its nucleus, and it's the number of protons that defines the element. It's only when two deuterium nuclei combine that a new element is created. Take two deuteriums and fuse them together, and you get a nucleus with two protons and two neutrons. That's helium, the second simplest element. And then it's just a question of adding more and more protons and neutrons. Having 12 of these bubbles sticking together would count as 6 protons and 6 neutrons. And you can go on, building more and more complex elements, all the way up to the heaviest elements in the universe, to uranium and beyond. This process of building the elements is called nucleus fusion. It allows the simplest ingredients to create the infinite variety of the universe. But although this bubble metaphor makes creating a new element seem simple, it is in reality incredibly difficult to achieve. So there's only one place in nature that it happens. It's in the stars, like our sun, that the elements are assembled. They are the only places in the universe hot enough and dense enough to fuse atoms together. Even then, only a fraction of a star reaches the extreme temperatures that's necessary. The Sun is 6,000 degrees Celsius on its surface, not nearly hot enough to power fusion. But deep below, where the temperature reaches 15 million degrees, the Sun fuses hydrogen into helium at a furious rate. Every second it burns 600 million tons of hydrogen. As it does so, it releases huge amounts of heat and light that brings our planet to life. It is this process that converts one element into another that allows us to exist. Of all its power, the Sun only converts hydrogen, the simplest element, into helium, the next simplest. But there are over 90 other elements present in our universe. So where did they all come from? If the heavier elements are not being made in stars like the Sun, then there must be somewhere else in the universe where they are assembled. It's important to know because it's the element beyond helium that gives our world its complexity. And when it comes to planet Earth and human beings, there is one element particularly important: carbon. Life is completely dependent on carbon. A human is made of a few billion carbon atoms, as is every human out there, every living thing on the planet. Just imagine how many carbon atoms that is. So where does all the carbon come from? It comes from the only place in the universe where elements are made: stars. But in order for us to live, a star must die. In the prime of their lives, like our sun, are only hot enough to make helium. Forming the heavier elements requires much higher temperatures. Temperatures that can only be reached at the end of a star's life. Looking out into space, you might think that the cosmos is a constant, unchanging place. The stars will always be there. But in fact, the stars are only a temporary feature in our skies. And although they might burn bright for many millions or billions of years, they can only live long enough as long as they have a supply of hydrogen to burn. When a star runs out of hydrogen, it begins to die. But it doesn't go quietly. Rather than cooling, the star becomes much hotter until there's a sudden flash. Then, the star starts to expand. Over tens of thousands of years, it balloons to many hundreds of times to its previous size. But in this bloated state, the star is unable to maintain its surface temperature. As it cools, it takes on a characteristic color of a dying star. It has become a red giant. These are pictures of a red giant star in our galaxy, a star called Betelgeuse. It is one of our nearest neighbors in cosmic terms. It's only about 600 light years away, but it's the size that's astonishing. If you had to put the sun in the middle of the star, you can fit everything in the solar system all the way out to Jupiter inside the star. Because it's so big, even though it's 600 light years away, you can see detail on its surface. So these are sunspots on the surface of Betelgeuse. But it's not what's going on the surface that's really interesting. To understand where carbon comes from in the universe, we have to understand what's going on deep in the heart of the star. In the heart of the star is where the core lies, and it's down there where all the ingredients of life are made. Deep in its core, The star is fighting a futile battle against its own gravity, as it desperately tries to stop itself collapsing under its own weight. New elements are made in a sequence of separate stages. Stage 1 is while there's still a supply of hydrogen to burn. While the star is burning hydrogen to helium in its core, vast amounts of energy are released. And that energy escapes, literally creating an outward pressure that keeps the star stable. But eventually, the hydrogen, the core, will run out, and at that point, the fusion reaction will stop. No more energy will be released, and that outward pressure will disappear. At that point, the core will start to collapse very rapidly, leaving a shell of hydrogen and helium behind. Beneath the shell, as the core collapses, the temperatures rises again, until at 100 million degrees, stage 2 starts, and helium nuclei interfuse together. A helium fusion does two things. Firstly, more energy is released, and so the collapse is halted. And secondly, two more elements are produced in that process: carbon and oxygen. Two elements vital for life. So this is where all the carbon in the universe comes from. Every atom of carbon in my hand, every atom of carbon in every living thing on the planet was produced in the heart of a dying star. To compare to the lifetime of a star, the creation process of carbon and oxygen is over in a blink of an eye, because very early, about 1 million years, the supply of helium in the core is used up. And for stars as massive as the Sun, that's where fusion stops. Because there isn't enough gravitational energy to compress the core any further and restart fusion. But for massive stars like Betelgeuse, the fusion process can continue. When the helium runs out, gravity takes over again, and the collapse continues. The temperatures rises once more, launching stage 3, in which carbon fuses into magnesium, neon, sodium, and aluminum. And so it goes on. Core collapse, followed by the next stage of fusion to create more elements. Each stage hotter and shorter than the last. Eventually, in the final stage that lasts only a couple of days, the heart of the star is transformed into almost pure iron. This is where the fusion process stops. In its millions of years of life, the star has made all the common elements, the stuff that makes up 99% of the Earth. The core is now a solid ball of those elements stacked on top of each other in layers. On the outside, there's a shell of hydrogen. Beneath it, a layer of helium, then carbon and oxygen, and all the other elements all the way down to the very heart of the star. Once that has fused into solid iron, the star has only seconds left to live. When a star is out of fuel, then it can no longer release energy for a fusion reaction. And then there's only one thing that can happen. In about the same amount of time it takes this building to crumble, the entire star falls in on itself. This is the destiny that awaits most of the stars in the universe. Yet, even the implosion of the star only forges the first 26 elements. What are the remaining elements? Some of which are vital for life, and many of which we hold most precious. This is what all the fuss is about. But there's something a bit odd to the value attached to gold. Throughout history, people have gone to extraordinary lengths to get their hands on this most precious substance, which is strange because it isn't particularly useful for anything. Most of the gold that's been extracted throughout history has ended up as jewelry. But it has got one thing going for it. It's incredibly rare. All the gold mined from the earth in all of human history will only fill 3 Olympic-sized swimming pools. It's that scarcity that makes gold valuable. But gold is just one of the many rare elements. There are over 60 elements heavier than iron in the universe. And some are valuable like gold, silver, platinum. And some are vital for life, like copper and zinc. And some are just useful, uranium, tin, and lead. But across the universe, there are vanishing small amounts of these heavy elements. The reason for that scarcity is that creating substantial amounts of the heaviest elements requires some of the rarest conditions in the universe. And we need to look far into space to find them. In a galaxy of 100 billion stars, these conditions will exist on average for less than a minute in every century. That's because they're only created in the final death throes of the very largest stars. Stars of at least 9 times the mass of our Sun. Only they can reach the extreme temperatures needed to create large amounts of the heavy elements. Deep in the heart of the star, the core finally succumbs to gravity. It falls in on itself with enormous speed and rebounds with colossal force. As the blast waves collides with the outer layers of the star, it generates the highest temperatures in the universe, 100 billion degrees. These conditions last for just 15 seconds, but it's enough to form the heaviest elements, like gold. This is called a supernova, the most powerful explosion in the universe. The most precious thing to us is the gold in a wedding ring, forged in the death of a distant star millions of light years away, billions of years ago. Despite the rarity of supernovas, when they do happen, they're the most dramatic events in the sky. This is the Tarantula Nebula, which is a cloud of gas and dust. Through the Large Magellanic Cloud, which is a huge cluster of superstars at the Milky Way. And this is what it looks like on any clear starry night of the year. But on one night in 1987, the Tarantula Nebula looked different. See that a bright star has appeared in the sky. This is a supernova explosion. The explosive death of a massive star, and they are incredibly violent cosmic events. This is a galaxy about 55 million light years away from Earth, with a supernova explosion in that galaxy. You can see it shining as bright as the galactic core. Yet, to really appreciate the scale of these explosions, we would need to see one up close. To see a star die in our own galaxy, the Milky Way. Although, on average, there is one big supernova in each galaxy every century, there hasn't been one in the Milky Way since the birth of modern science. The last was in 1604, so we are long overdue. Astronomers are now searching the skies for the star that is most likely to go supernova. And amongst the leading candidates, there's a familiar name. This is the constellation of Orion, and this is Betelgeuse. We all know that it's extremely unstable, because it's dimmed by about 15% in the last 10 years. Now astronomers think that this star could go supernova at any moment. That could mean any time in the next million years, but equally, it could explode tomorrow. And Betelgeuse is at least 600 light years away. When it goes, Betelgeuse will be incredibly bright. It will be by far the brightest star in the sky. It may shine as brightly as a full moon. It will be almost a second sun in the daylight. In this single instant, Betelgeuse will release more energy than our Sun will produce in its entire lifetime. As the star is torn apart, it will fire out into space all the elements that it created in its life and death. Those elements will spread out to become a nebula, a rich chemical cloud drifting through space, and at the heart of the nebula will be a tiny beacon of light. The remnant of a star once, more than 1.5 billion kilometers across, that has been crushed out of all recognition by gravity. This is Betelgeuse, the neutron star, and it's how this once mighty star will end its life. Once Betelgeuse is gone, the constellation of Orion will look very different. There will just be a hole in the sky where that brilliant bright red star once was. But it's in the deaths of old stars that new stars are born. It's very much like the cycle of death and rebirth here on Earth, played out on a cosmic scale. And you can see that happening today in the constellation of Orion. In the sword handle you can see this. The Orion Nebula. Now that is nothing more than a misty patch of light in the night sky to the naked eye. But if you look more closely, you see that there is a lot more going on. The Orion Nebula is one of the wonders of the universe. Hidden in its clouds is the bright points of its lights. These are new stars forming from the elements blown out by supernova explosions. New stars being born from the remains. And it's from this universal process of death and rebirth that we emerged. Because it was in a nebula just like this 5 billion years ago. That's how our Sun was formed. Around it, a network of planets formed. Among them was the Earth. Everything we find on the Earth today also originated in that nebula. But that is not the end of the story of how the universe created us. Because when we look deep into the nebula, we don't just see individual elements. We see greater complexity, the seeds of our own existence. The spectrum of light of the Orion Nebula shows that gas clouds is not just a cloud of elements. It's complex chemistry happening here in deep space. It shows there are some molecules present that are quite obvious like water. But there are also complex carbon compounds in here. There's methanol, hydrogen cyanide, and formaldehyde. So what we see here is complex carbon chemistry happening in deep space. That carbon chemistry is the beginning of the chemistry of life. And there is surprising evidence that this chemistry may have had a direct impact on the evolution of life on Earth. That evidence comes from meteorites, debris left over from the formation of the solar system that occasionally collides with the Earth. A piece of meteorite that fell to Earth from somewhere out there in the solar system is certainly older than any rock you can see here. It's probably older than any rock you can find anywhere on Earth, because it formed from the primordial gas cloud, that nebula that collapsed to form the Sun and the planets over 4.5 billion years ago. It's incredibly ancient. Inside a meteorite, you will see little brown areas where amino acids were found, the building blocks of proteins, which are the building blocks of us, the building blocks of life. Incredibly complex carbon compounds. This complex carbon chemistry you need to send you on the path to life was happening out there in space 4.5 billion years ago. So, the first amino acids on Earth, the fundamental building blocks of life, may have formed in the depths of space and been delivered to the Earth on meteorites. When we look out into space, we are looking into our own origins because we are truly children of the stars. And written into every atom and every molecule of our bodies is the entire history of the universe, from the Big Bang to the present day. Our story is the story of the universe. Every piece of everyone, that everything you love and everything you hate, or the thing you hold most precious, was assembled by the forces of nature in the first few minutes of the life of the universe. Transformed in the hearts of stars, are created in their fiery deaths. And when you die, those pieces will be returned to the universe in the endless cycle of death and rebirth.